Good afternoon. And this question is about the unit for the pressure. There are many different units. This question is about the unit which is a part of an international system of units. And here we also see an illustration which tells us that force distribution, pressure might be important. Imagine that the same person meaning same weight. So if that guy falls on one single sharp object, a sword, for example, done, he's dead. But if the same person lies on many sharp objects, that's a standard demonstration, has a name, bed of nails. Well, that has a name as suicide. Years ago in Japan, for example, people did that in order for not getting caught by the enemy. So, but the difference is basically life and death. And again, the force is the same, same person, same mass, same force of gravity, but the distribution of that force over the area makes a big difference. And the equation, the definition of the pressure, the equation at the top tells us this is the name of that unit, pascals, but this is the definition. To measure force, we have to use newtons. To measure area, we have to use meters squared. So the correct unit is the last one, Newton over meter squared. And the name of the unit pascals is because of the physicist and the physician who did a lot of research. In particular, there is a law or principle which tells us how the pressure applied to a fluid being distributed. Well, we treat all fluids as ideal. There are more conditions to be an ideal fluid. One of these conditions is incompressible. So we cannot change its volume. We can't compress it. And in this situation, this is an example of hydraulic lift or hydraulic press in a similar way can work. It's very similar to a mechanical lever. If we apply the Pascal's principle, we have to make a conclusion that the pressure we applying here and the pressure which the liquid, normally it's oil, applies here has to be the same because, well, if there's no change in the volume, the pressure has to be transmitted. And as soon as we said that, the rest is very simple math. By definition, the pressure equals force over the area. So we can amplify the force. The force number 2, for example, going to be equal to the ratio of two areas times the force number 1. So this number, if we maintain this number to be relatively large, the force we can achieve will be, well, in this example, 10 times stronger than the force we are applying. And if we apply the same principle to a situation like that, we can start from writing the same expression, and that's going to be the force which we want to generate, but the force which is actually pushing here supposed to be related by the Pascal's principle. And the force you should apply, this one, well, that's the axis of rotation. Yeah. Two forces, lever arm, you know what to do. Now, this slide demonstrates how we can calculate the pressure. First of all, which pressure, which kind of a liquid. So far, we talk about the static liquid only. Static means no motion. And if we use a static, well, of course, when I pour it into this simple device, liquid is moving, but we let it rest, settle. Too much, too much, too much. All right. I've got the backup. Anyway. When it settles, you can see it doesn't matter what kind of a shape is it, wide, narrow, the level is the same. So the pressure in a static liquid depends only on the height. Well, at the open surface, of course, it's opened to the atmosphere. The pressure is atmospheric here. And below, the pressure goes, well, up higher and higher and higher, depending on how much liquid is above a certain level. So this equation on the slide tells us how we can calculate that pressure. Maybe not, no? So we go deeper and deeper and deeper. What can you do? You can you can take a scale, put some, diving suit, scuba, and dive. And if you go deeper and deeper, you can read the reading. It goes up because pressure goes up. But there is an easier way, which we used last time. You put a scale, a beaker, and you pour water. So the more water you pour in, the more force you read, and the force divided by the area gives you pressure. And that's exactly what has been done here. This is the force of gravity acting on this water column. Force divided by area is equal to pressure. So it turns out the pressure to this column is equal to density of this fluid times 9.8 if it's on the Earth, times the height of this column. If we go below the surface, we would call it deepness, how deep it is, right? But still, that's a water column or oil column, and that's how high it is. But that's what we call the gauge pressure. The pressure due to purely this amount of liquid. Above this, we might have a different liquid, oil on water, for example, or gasoline on water. Or if there's no other liquid, there is atmosphere. It's also a fluid, a gas. So the actual pressure, the total pressure, should include the pressure at the surface, well, normally atmospheric pressure, plus the gauge pressure, this one. And when we read the problem, very common, we don't know what they mean. The pressure at the bottom of the lake. What pressure? Total. Gauge. We don't know. It's, well, ambiguous. The author wasn't very clear. So what do? We try both. We have 6 trials. 2 should be sufficient, ideally. So first, I would usually assume they mean gauge pressure. And if the gauge pressure doesn't work, I would add the atmospheric pressure. and see if that works. Just to illustrate one more time, so actually, this particular phenomenon. So you see this tube, we don't really actually see it. Well, you can see it right here. This tube is open to the atmosphere at both ends. Of course, static liquid, so atmospheric pressure here, and then equal pressure here and here, here and here, same level, same pressure. How can I break it? Well, I can try to shift one of the branches of this U-shaped tube. For example, I can try to move it higher. Nothing. Lower. Still nothing. So what do I have to do? Well, if I move it up or down, of course, because it's open to the atmosphere, the pressure balanced out. So all I want to do is have some fun. I've got a feeling I'm not the only one. So now there is no connection between this atmosphere and the gas inside. Right now, of course, the pressure inside this part is still atmospheric. But what's going to happen if I start moving? Well, you see, now it breaks. So where is the atmospheric pressure now? Oops. Well, here is still atmospheric. It's leaking. It's over here. What about now? Okay. So where is the atmospheric pressure now? Well, there's a red mark right here. It's above this level. So same level, same pressure, atmospheric, atmospheric. Here, we should have atmospheric pressure. But this pressure should be equal now to the pressure due to this column, gauge pressure of this, plus the pressure inside this. See? And of course, if I open it, the balance will be restored immediately. We just have to wait a little. This is, how do we call this motion? Oscillations. That's actually a simple harmonic motion. We can solve the period, frequency, everything. But because, of course, there is friction, it eventually stops not moving anymore. So this is how the atmospheric pressure has been measured historically the first time in the history of life, physics and people, you know. So the physicist Torricelli, Italian physicist, he just took a very long tube filled up with mercury, then flipped it over and let it flow out. But eventually he has noticed that some of the mercury stays inside the tube. Now, why is it happening? Well, because the pressure due to this column, the gauge pressure of the mercury, balanced out by the atmospheric pressure. So we can actually calculate now the gauge pressure of the mercury, convert it into newtons per square meters, and that's going to be atmospheric pressure. It, of course, has been done many times. And there are different units. Again, Torricelli, millimeters of mercury, 1 atmosphere. When we do problems, we don't usually use 1.01. We just set it to 10 to the 5th pascals. All right. Next question. It doesn't have to be a tank, a bottle. There's a hole in this bottle covered by this tape, and there's a cup, so I can open either of these two stoppers at the bottom, at the top, and what I want to do is open this one first. So I take it out. What do you think should happen? So choose your answer. Keep pressing. And when I push on it, okay, that's it. See? See? Anything? Nothing. Of course not. We need 760 millimeters of mercury to achieve atmospheric pressure. So this is not mercury, regular water. Mercury has density 13 times more than water has. So to balance out atmospheric pressure, we need like 10 meters of water. Of course, that's not 10 meters. So the pressure from inside is not enough to push the water out. Well, what's going to happen if I open the second one? Now, of course, the pressure here and the pressure here is atmospheric. The open surface should have the atmospheric pressure, so the only gauge pressure now matters and results in this water flowing out. And we actually can solve, and we will solve very soon, what is the speed of that water which is leaving this bottle. Good thing we don't have to use mercury anymore. All right, so what did you say? What was number 3? Cancel. Number 3, what was it? Nothing. Yeah, but what was number 4 in that case? All right, so we know how to calculate the buoyant force. The expression for the buoyant force has been derived experimentally from measurements. But now, we actually can prove it purely theoretically. First, we should use the equation for the force. And now we have to apply our knowledge of mechanics. So if an object is in equilibrium, net force has to be equal to 0. Here, it's not, well, forces from a side cancel each other out, horizontal forces. When we're closer to the surface, force is not so strong. We go deeper, force getting stronger, but there is an opposite, so they cancel. But force at the bottom is stronger than the force at the top due to higher pressure. So now here we have force which first of all points up, and if we finish our calculation, that of course gives us the density of this liquid, the volume of that object, or that part of the object which is in the liquid, and G, gravity 9.8. So now, as I said, we talk about only a specific case, an ideal fluid, which means we can't compress it, also no friction, no turbulence. In this situation, we can simplify our reasoning significantly. So let's say you have a fluid traveling through a pipe or tube. If it cannot be compressed, that immediately means that the same amount of liquid travels every second, everywhere, through every cross-section. The same amount of liquid should travel. Doesn't depend on the size of the pipe. Doesn't depend on anything else. It's a property of the liquid. This amount, which travels every second, has a name, mass flow rate. And by definition, it's just how many kilograms per second travels through any cross-section. And as we said, because this liquid is ideal, the mass flow rate is the same everywhere, constant. Now we can make a next step, because again, we cannot compress this liquid. Density also doesn't change, stays the same. We can cancel the density, and what's left is this equation, which has a name, the continuity equation. It relates the speed of the fluid and the area of the pipe. And this product for an ideal fluid has to be the same, no matter what. It is, again, just derived from a property of an ideal fluid. And to make it flow, normally we would have to do two things. Either, well, we use force of gravity, we pour, and the liquid kind of fall down, or we pump it, have a piston or an actual pump. So in that situation, if we treat each individual portion of this fluid as a single particle, we also can apply our knowledge of mechanics. For example, we can write the law of conservation of mechanical energy or work kinetic energy theorem, as we know same things. It's just because it's not a single particle, it's a large amount of fluid travels, we don't write it for the whole fluid. It's impossible, it's too large. So we write it for 1 cubic meter of it, that's it. So if we choose 1 cubic meter of this fluid, the mass of that cubic meter is equal to the density of it, that's it. So we can take this equation divided by volume, or we can just replace mass with the density. And that's the law of conservation of energy for the fluid, an ideal fluid, no friction. And we can rewrite this law differently. Well, this equation is literally work kinetic energy theorem applied to 1 cubic meter of a fluid. That's it. But if we rewrite it, as we did in mechanics, if we collect all terms related to one location on one side of the equation, and we collect all terms related to another location in a pipe on another side, that looks more like a law of conservation of mechanical energy, which is exactly it. That is the law of conservation of mechanical energy written for 1 cubic meter of that flow. This equation has a name. This equation has no name. This equation called Bernoulli's equation. So now, for any ideal fluid, static or moving, we always can apply two equations the continuity equation, and Bernoulli's equation. That's it. These two equations describe all possible problems, all possible situations related to static or moving fluid. Basically done with the theory, nothing else to say. So I'm going to give you a minute, and I want to ask you this. You see, the mass flow rate equals density times volume flow rate. So first we have to calculate the volume flow rate, and then if you want to, we can multiply by the density. That will give us the mass flow rate. But the volume flow rate here should use liters per second. So 1 minute. Volume flow rate. Volume flow rate. If you say it fast, it sounds like volume flow. No, volume flow rate. "40 seconds. You know that you have, I don't know, like 55, 60 seconds to solve it, and last 5 seconds to press a button, whichever you choose. Yeah. And of course, because we are solving a physics problem, what do we do first? Well, again, lesson 1 strategy always the same. We read and we draw a picture first, and then answer number 2 is correct. So this is a rectangular pipe. So water flows, the speed is 2 meters per second, 10 centimeters, 10 centimeters. So all we have to calculate is, well, for the volume flow rate, 10 centimeters times 10 centimeters, that's the area, times, and I want to keep centimeters, 200 centimeters per second, because it's much easier to convert centimeters into liter, centimeters cubed. So what we have is 2,0,0,0,0 cubic centimeter divided by a second. Now, how large is 1 liter? 1 liter is a volume which equal to 10 centimeters by 10 centimeters by 10 centimeters. That's 1 liter. So 1 liter equals 10 times 10 times 10, 1,000 cubic centimeters. So if you just take out last 3 zeros, that gives you liters automatically. Now, what about mass flow rate? Well, the density of water, we know it equals 1,000 kilograms per cubic meter. We know it equals 1 gram per cubic centimeter. How heavy is 1 liter of water? One cubic centimeter weighs 1 gram. 1,000 cubic centimeters, 1,000 grams or 1 kilogram. So that's a convenient fact. 1 liter of water weighs exactly 1 kilogram. So mass flow rate will be this. Water is moving. Okay. So take a picture in your save it in your memory. Hose, water. What does water mean? This word means density equals 1,000 kilograms per cubic meter, or 1 gram per cubic centimeters, or 1 kilogram per liter. So the diameter is 2 centimeters. Well, okay. Volume flow rate is equal to A times V. Well, area now is circular, so pi, diameter over 2, don't forget parentheses squared, times V. Don't want to calculate, just write down numbers. 2 centimeters divided by 2 squared, and 5 meters per second, 500 centimeters per second. Actually, even easier, 2 over 2, 1. Pi is about 3. Let's keep it 3. Let's forget about 14. So it's about 1500 cubic centimeters per second. 3 decimals, 1.5 liter. About. I rounded up pi to just 3. You can do a calculation more accurately, and the mass flow rate will be about 1.5 kilograms per second. Now you attach a nozzle. So it's a garden hose. You're touching a nozzle. What will be happening to the speed of the water? So when leaving the nozzle now, because it's narrower, water should travel faster. So if we call it point number 1, if we call it point number 2, so V1A1 should be equal to V2A2, the continuity equation. And it absolutely doesn't matter if we hold it horizontally or vertically or we bend it. It is irrelevant. We just have to connect 2 points, number 1, number 2. That's it. That's the connection. So 5 meters per second and times pi times 2 centimeters divided by 2 squared should be equal to speed number 2 times pi times diameter number 2 divided by 2 squared. Actually, the speed number 2 also is given 10 meters per second. So what can we do? 5 over 10. Pi cancels. See how many things getting cancelled? Pi. These two. Well, meters per second. And here we have left 4 centimeters squared. And we should take a square root of that to calculate the diameter of the nozzle. Square root of square, so that gives centimeters. And the number, well, 5/10 is 1/2, so 4 divided by 2 is 2, so square root of 2, about 1.4 centimeters. Where are we? Okay, now you take the nozzle off and you attach a shower cup. How does it look like? Well, something like that. So the same hose, and now you have basically a cover with many, many holes. How many holes? 30. And each hole has the same diameter, 5 millimeters. And now the question is, what is the speed of water leaving each hole? Well, again, we can apply the continuity equation. That's the area number 1, that's the speed number 1, that's the speed number 2. Question is, what should we use for the area number 2? Well, the water living through all 30 holes. So the area number 2 should be equal to the number of holes times the area of a single hole. That's it. Now we're all set. So 5 meters per second times pi times 2 centimeters divided by 2 squared. Same volume flow rate, of course, has to be equal to 30 times pi times, well, if I use centimeters, 5 millimeters, that's 0.5 of a centimeter divided by 2 times V2. So again, we can cancel pi, 2 and 2. Centimeters and centimeters squared getting cancelled. So what do we have? V2 should be equal to 5 meters per second, that stays, divided by 30, and 0.25. Now, this is 5, this is S, this is 5, this is 2. So that's basically 20 over 30, 2/3 of meters per second. 5. Oh, I forgot 2. 2 squared, 4 times 4 times 4, 8 thirds, right? Check me. So 5, 2 squared, that's 4, 0.5, 0.25 over 30. Yeah, now it works. Right? Yes or no? Yes. All right, we know what's going to happen. We know when both holes are open, just water leaving this tank or wherever it is. Now, we know that when a surface is open to the atmosphere, the pressure at that surface has to be equal to the atmospheric pressure. Well, if it is related to the pressure and the height, that means we have to start from Bernoulli's equation. And we should choose the origin at the lowest position. That's so the point number 1, atmospheric pressure plus density times speed squared divided by 2 plus density times gravity times 0, because there is no height, equals, again, atmospheric pressure, well, plus density multiplied by V squared over 2 plus density G times height. Well, this height, H, is equal to 3 meters, we can read. And because both surfaces are open to the atmosphere, same pressure, getting cancelled, that's also 0. So the only question is about speeds. And, well, strictly speaking, we should do this. A1 V1 should be equal to A2 V2. To use this equation, we need to know this ratio. Like V2 is equal to A1 over A2 times V1. If we know this ratio, we have two equations and we have two unknowns. V1 is the unknown number 1, V2 is the unknown number 2. And we know this ratio. If you look at the picture, this surface, A2, is huge. And the surface at the location of the hole is tiny. So this is a general assumption we always have to do if we don't have exact information about the diameter or about the area. So if this, well, is a valid assumption, this ratio, A1 over A2, will be very, very small number. Much less than 1. So what do? We neglect it. So V2 supposed to be equal to V1 divided by a huge number. So it's practically 0. So every time when one surface has a very large area and another surface has a very small area, we can neglect the motion of the large surface. So basically we say that V2 is practically equal to 0. That's what we say. Of course, that's not always the case. Of course, in reality, it moves. But if it's a relatively large tank, we should wait a long time to see the significant difference. However, if this approximation works, what do? We cross out one more term. And what's left is a simple equation. This equals this. Turns out density doesn't matter, getting cancelled. And the final expression for the speed actually is nothing new. Exactly the same expression we had for the ball falling down or for the cart rolling down the ramp. If there is no friction, if everything is ideal, the law of conservation of energy tells us that's what should be the speed. That's it. Very simple. Huge pipe. All right. Let's do a picture. So there's a ground, and on the ground level, there's a pipe. Let's call it point number 1. This is going to be the diameter number 1. Water travels here at the speed number 1. Diameter number 1 is equal to 40 centimeters. And this is an unknown. Then it bends. There's a huge tank. We have to fill it up with water or oil, doesn't matter. So we have to bring the pipe up. So it's opened here. So here, the pipe is very long. So it must be a pump somewhere pumping in. So this surface, number 1, is not open to the atmosphere. But this is, water just flows out of it, filling up the tank. So here, there's a speed number 2, also an unknown. But the pressure number 2 is supposed to be equal to the atmospheric pressure, which is 10 to the 5th pascals. Now, this pipe goes 20 meters higher of the ground. 20 meters. H equals 20 meters. That's what we call, H2, Y2. And of course, Y1 is set to 0. That's the lowest point of it. And the diameter now, the diameter number 2 is equal to 80 centimeters. That's it. No, one more number. The pressure at the bottom, right here, P1, is equal to 2 atmospheres, which means 2 times 10 to the 5th pascals. What do we do now? We have only 2 equations to use to write. So we have to write 2 equations. V1 times A1 equals V2 times A2. And the second, P1 plus kinetic energy plus potential energy. Let's call it Y. Has to be equal to the pressure number 2 plus kinetic energy at the second end of the pipe plus potential energy. 2 equations and 2 unknowns. V1 is an unknown, V2 is an unknown. Unfortunately, these equations, well, one of these equations is a quadratic equation. So that makes math hard. But again, math is outside of the scope of this course. Any questions? These are just illustrations of how we solve problems related to moving fluid. We're just writing 2 equations again and again and again and again and see what's going to happen. All right. Look at the levels. Come on, wake up. Well, okay. You can see it. Same levels, different levels. Well, first of all, same level means the pressure is the same. Different level means the pressure is different. And where should we say the pressure is higher? Of course, here. It's like extra push to move it down. So, but this is wider, and this is narrower. Why is it happening? Because of Bernoulli's equation and continuity equation used together. Here and here, same diameter, same speed. Same speed, same height, same pressure. Here and here, more diameter, so if it's wider here, it should travel how? Slower. And here it travels faster. But the height is the same. So the pressure here should go up, and the pressure here should go down. And in a lab, some of you already have done a similar experiment. So let me show you one more time. That's actually not a ping pong ball. This is actually a heavy golf ball. And still, the pressure difference is strong enough to prevent it from falling down. Why? Well, when the airflow goes like this, above the ball, because of the friction, it travels slower. Let me see. No, it's practically not moving below. So because it's like making a shadow. So below this ball, just a sec, I have a picture. Below this ball, there is practically no motion, so there is a pressure difference which moves it up. Here, oops. So the practical applications of this particular phenomenon are huge. And I don't want to do it next time, so I want to do one more demonstration. It's going to take just a minute. Because again, in the lab, you've done exactly the same demonstration. My device is just much more powerful. There is nothing to wonder about this. This is a so-called lift. Yeah, this is why airplane flies. Again, there is a pressure difference because speed above is higher, lower, to pressure higher, lower, and that's why we fly. All right, now we're done. Thank you. What's wrong? Yes.
Did you say that people can miss one lab or two labs?
I never said that.
Oh.
What I said is seven best lab grades out of 9 will be used for calculating the final grade. That's what I said.
All right. Thank you.
can you just bring it over there?
Yeah.